your solution from the column is coming through rich in bicarbonate, as well as the anions you're trying to separate, which aren't shown here. Okay. And you're using a sodium bicarbonate. So you have bicarbonate as well as the cations come in as part of your element. Right? On the anode, in this space on this side of the cation exchange membrane, the potential is oxidizing water against this anode and oxidizing the water into oxygen and protons. And if you look closely at the tube coming out of the suppressor in the instrument, there's a tube that's taking the regenerating solution from the suppressor that's recycling it. And if you look closely at it, you see a lot of air bubbles in there. And those air bubbles are the oxygen that's being formed by the oxidation of water at this anode. So in producing all the oxygen and then all the protons, which matter, the protons are able then to diffuse across, from a high concentration to low, diffuse across this cation-specific permeable membranes into the eluate space where your column eluate is going. Those protons then combine with the bicarbonate to form carbonic acid, which is no longer conducting. Okay. The sodium cations are able to diffuse across the membrane, because they're also ions that would contribute to the conductance in the detector, diffuse across the cation permeable membrane, and essentially into this regenerated space, they're being drawn by electrostatic attraction to the high hydroxyl anions in here. They diffuse across into this space, and they're essentially flushed out and regenerated. So in this process, you have all your anions coming through, including a high concentration of bicarbonate, and the bicarbonate is then combining with a relatively high concentration of protons that are diffusing and immediately reacting at this surface with the bicarbonate to form carbonic acid. And it's non-conducting, and the sodium is diffusing out. So you're depleting this space of the interfering anion and the high interfering cations before it flows out and into the detector. And so when you turn the suppressor on and off, all that's doing is providing the potential to the anode and the cathode to start this electrolysis.
And this is happening along the column?
This is happening
after
the column. So if you look at your instrument, this is it right here, right? And so the tubing, you can't tell from this, I'll say, but you know, you inject your sample, it goes through the sample loop, and then it goes, winds the tubing, it goes through your column, the guard column, which is over here, I think, or here, it looks just like, maybe they show it here, but it really, in yours it's over here, I think. It goes through all that, and then it enters the suppressor, which is this. And then after the suppressor comes out, it enters the detector. So it's a nice bit of chemistry that allows us to increase, increase the sensitivity by at least an order of magnitude in measuring the anions. Right? And it works basically the same way, whether it's a bicarbonate buffer system that you're using, or whether it's a potassium hydroxide, different kind of buffer system.
Why does this not remove other anions from the elements?
It's a good question. Why is it removing other anions from the eluate coming out of the column?
So when you go to the column, does the anions bind to the mobile phase?
When you go through the column to the anions, so the anions are in the mobile phase.
Yeah.
So I'm not sure I'm following this. Okay, so why? Well, that's an important thing. Why is it that you are not altering the levels of other anions in there?
Most of them not really all that basic.
Because they don't have the same pKa that the carbonate bicarbonate does, right? And so by having this solution with a pH of about 6, you have a fair amount of this that can react quite readily with even the slightest increase in protons, and it's going to shift it that way. Right? And so it's because that you are operating this buffer system at a pH that's around this pKa. It's a very sensitive buffer system. You only change in this, which is what you're providing. Right? But the other anions, if you were to substitute this for chloride or fluoride or sulfate or whatever, they're not so reactive with those protons, and they certainly won't form, they're not function as a weak acid or a weak or a base. So they're not reactive, that's why. Okay, does that make sense? You guys got that? Because we're gonna ask you in your report to talk briefly about the suppressor and what role it plays. One thing for lab report number 2 and number 3 that you're going to expand upon from the first one is a much more developed discussion of the instrumentation, the theory of the instrumentation, and how the different components work that are essential for the function of that method. And the suppressor in this case for exchanges. Okay, so the detector on this is like we talked, is measuring conductance. Right? And conductance is essentially just the movement of electrons from one side, one pole of the detector, one side of the volume of that cell to the other. And of course, things that have higher conductance would be analogous to things having higher concentrations of dissolved ions in the solution in which to conduct that current from one side of the cell to the other. And so the problem with these detectors, and the reason that a suppressor is needed, is that they're considered to be bulk detectors. And bulk means that it's measuring the bulk conductance of a current across those poles in the detector, and it's not specific for any particular anion or anything. It's just basically measuring the extent to which that solution can conduct, this passage can conduct a current across. I think that's what we mean. And when we think about conductance, there's two things that we have to consider. One is whether the current is going to pass across the poles, conductance, or whether it's not. Of course, that's resistance, right? And in direct currents, electrical circuits, we talk about resistance, and resistance, of course, is the inverse of conductance, right? But in alternating current electrical circuits, like what we have here, it's plugged into the wall, right? EC circuits. It's not resistance that really is determining the conductance. It's actually the impedance. So resistance is applicable in direct current circuits, and impedance is applicable in alternating current circuits. And the reason that they, aside from that we all have AC currents coming out of our walls, the reason that this doesn't have a transformer to convert the AC to DC is because in conductance detectors that are operated under a DC current circuit, over time there's a polarization of the poles, and there's a drift in the baseline that becomes noisier. So it's not as effective as a electrical circuit controlling conductance detectors if they're direct current circuits that are wired into compared to their alternating current circuits. So all that matters for us then is thinking that I have two processes that are essentially at play here. I'm measuring conductance with my detector, but what is determining conductance is really the amount of impedance or resistance to the passage of current from one detector to the other. Okay, does that make sense? And you could think of it like a river, and the river is the conductance, the movement of the water, and the river is the conductance. But what determines how much water can move down the river are the things that are in the way of the water moving, whether it just be debris in a river or a dam in the river. And so those are things that are providing impedance to the flow of the water of the current, just like this. So in your solutions, the absence of ions is what is providing the impedance. Because water itself is not a very good conductor compared to water that has dissolved ion. And I say all this there, so a little bit. All right, so now if we look at this whole system put together in sort of a cartoon form, we know now, if you were to draw this, you know how you start with your eluate that has certain concentrations of a buffer system that you are now very familiar with, and will become even more familiar. That buffer eluate is pumped through a series of two pumps that are very effective at pumping without any pump oscillation and under relatively high pressure. They go through a sample loop, in which you've loaded your sample, in which case it's 25 microliters. These are details that you want to make sure you make note of, because that determines how much sample is put on the column, obviously. If you want more sensitivity, you could, in principle, change that out, and we have multiple sample loops, and put in a 50 microliter sample loop, or a 100 microliter sample loop. Right? But yours is the 25 microliter sample. And then it goes to the guard column. And the guard column we talked is the same material as the analytical column that you're using, but it's much smaller. And the idea is it's not necessarily supposed to facilitate separations, but it's supposed to help protect the analytical column from the inadvertent injection of samples that have high concentrations of particulates or things that may clog the analytical column. And the cost of the guard columns are relatively inexpensive compared to the cost of the analytical column. And then it goes to the analytical column, and then it goes to the suppressor we talked about, where you remove the influence, the conducting influence of the bicarbonate and sodium ions, and then it hits the conductivity detector, and then you get your kinetic ring. So you'd be able to put all these components together and understand what role each of those are playing, and which ones you will have control over in terms of selecting as an analyst.
What's the guard column made of?
What's it made of?
What is the guard column made out of?
It is packed with the same material that's in the analytical column. And so, so it's packed with a stationary phase that has quaternary ammonium functional groups on it.
So why is that one much cheaper than?
Because it's really tiny.
Oh, okay.
It's small, it's not this big, and the analytical column's not that big.
Okay.
Yeah. And for the guard columns, you typically, they fit in, a lot of times they fit in a little housing, and it's like buying a little cartridge. You can unscrew it and put it in, and change them out pretty easily.
We have to keep that in mind when we calculate use the length of the column to calculate?
No, because the guard column doesn't really facilitate separation.
Okay.
Why doesn't it separate out the anion if it has the quaternary ammonium ions in it?
Because it's so small.
Oh.
It's just small, that's why. So it's meant to kind of be there, not to change anything. That's why it always meant, for guard column, you should always match the stationary phase of your analytical column, match that in the guard column, so that you're not have competing kinds of processes. But it's so small that not much can happen over that space before the sample moves through. And not all systems have guard columns, only the ones that, the people that are smart that have learned the hard way, that it was expensive to replace them. All right. So I mentioned before, I said, there's a lot of applications that different companies develop, and their bread and butter in developing applications is developing columns to meet certain applications. And sometimes people from this class go into environmental consulting kinds of positions within environmental consulting companies, where they do a lot of analyses of environmental samples, samples from wastewater, effluents, a whole variety of things they have, where there's a lot of monitoring that's required because of EPA regulations and so on. And so companies like Dynex and Waters and others, they actually have a business where they have labs of research staff who spend their days developing analytical methods to be able to separate and measure things with increasing sensitivity and specificity to be able to utilize in these industries that are doing all this water monitoring, or whatever they're monitoring as part of some government regulations. And this is just a web page, it's probably a year or two ago, but this is just a web page, part of it, of looking through it. Each of these are application notes for different kinds of methods. Direct determination of fluoroacetate water by CEMS, sensitive online SPE, HPLC, determination of paraquat, diquat, drinking environmental waters. So they actually spend time developing these methods, testing things, changing the parameters of their chromatographic methods in order to optimize applications. And then they write these up in these nice little method papers, and they post them so that people like you or me who are doing this could then adopt one of these methods in the job that I have to measure these samples. And the advantages, of course, it's a two-way street. The advantage is that they're doing a lot of the R&D for us in the industry, And of course, all these methods are based on Dynex columns. And so we write our column. And the one caveat with chromatographic methods is that they're really specific to the column, because all the action happens to the column, and there's a lot of chemistry and black magic that happens there that sometimes can't be easily explained by chemical theory. And so some of these methods are developed empirically, meaning that we try this and we modify this, and we modify the mobile phase and a number of things to facilitate a very specific kind of application of separating specific kinds of compounds. And so the end result of that is that, buying a column from Dynex with a quaternary ammonium group to do a particular separation will oftentimes work differently than if I bought a similar kind of quaternary ammonium column from another manufacturer, because they're all slightly different. And so there's a great niche in developing these kinds of methods, and there are pages and pages of these kinds of applications that these companies publish. There's a tremendous amount. Okay, so now let's back up a little bit. If we think of liquid chromatography, and the methods we were just looking at from Dynex, that's not, of course, just applying to ion chromatography. That's across different kinds of chromatography. And so I think we want to get a clear idea of these different forms and how they're used and what the basic separation processes are, because this is kind of what drives what we might start thinking about if we had to adopt a methodology. You graduate here in June or whatever, and a lot of times, like I said, students get jobs out of school with laboratory experience like this in some kind of analytical chemistry lab in the private sector. And a lot of times they join a lab and they're tasked with modifying or developing a method to measure something in some kind of sample. And oftentimes that involves some kind of chromatographic method. And so the first step is trying to get a sense of what is it I'm trying to separate and analyze, and what are the chemical properties of those compounds that I'm trying to separate and analyze. And then based on what I know about their chemical properties, I can then start selecting what might be the most appropriate chromatographic approach. And so chromatography is all based on, and we've talked about this a lot, chromatography is all based on a column, and it's based on the interactions of the stationary phase with the interactions of analytes inside the mobile phase, right? And it's this interaction that is facilitating the separation of this analyte from some other analyte in that column, which is their whole point here. And so if you know the chemical character of your analytes that you're trying to separate, then you can select what might be the most appropriate chromatographic approach. And so there's probably 4 or 5 different primary methodologies used in chromatography based on the kind of chemistry that's occurring in the column in the mobile phase and the stationary phase. And I'm going to go over those quickly, what they are. In all cases, of course, the column is a tube, and it's packed with beads, typically, very tightly, that have functional groups on those beads that impart certain chemical characteristics to that stationary phase. So in the case of normal phase chromatography, what that's talking about is that you have 2 basic kinds of processes that are driving separations, right? And one of the most basic chemical parameters or characteristics of a chemical that's used to separate is whether it's polar or not polar. Right? And so normal phase and then reverse phase chromatography is all talking about the polarity of the stationary phase relative to the polarity of the mobile phase. And so in normal phase, the stationary phase is polar, and the mobile phase is the opposite, non-polar. And now, depending on what the chemical characteristic of the molecule is, it'll partition more strongly in one or the other. You would vary these parameters of mobile phase to sort of select that degree of interaction. With the reverse phase, it's just reversed. And where the stationary phase is nonpolar, like a carbon chain, and the mobile phase has polar characteristics. Very simple in that sense. It's very complicated how things behave in there, but the basic of it is just as simple as that. Let's see that. Size exclusion is a very common method. And size exclusion, just like the term suggests, is separating analytes based on their
Size.
size, right? Based on their size. And how does it do that? Size exclusion is typically done where you have these porous beads, kind of like a wiffle ball. Does everybody know what a wiffle ball is? Yeah? When you're like, whatever, 10 or something. Okay, and so this column is packed with these wiffle balls. Those are not fairly tiny beads. They're hollow, and these beads have different diameters of pores in them. You buy this size exclusion gel or beads depending on what pore size you're looking for, right? And so you have a column that's packed full of these things, these wiffle balls, with a pore size that's selective for a particular molecular weight size, based on what your separation is. And so, let's say you're trying to separate things that are, these are for larger things. These aren't for dissolved small compounds. These are for things usually in the 2,000, maybe up to 100,000 Daltons, right? Molecular weight. So these are biological molecules typically that you're trying to separate, not small anions. And so you can have a range of maybe 2,000 to 10,000 for the mean diameter of this pore. Maybe from 10,000 to 30,000, maybe from 30,000 to 60, you know, so there's different size ranges of the pore diameter, the average pore diameter in these beads that are packed in the column. And then you load your sample on, and I'll draw one that's bigger now, so you can see it. You load your sample on, and the things that are small, well, smaller than the pore size of these beads, these wiffle balls, will travel through and get inside those pores and finally come out, because there's a net flow this way. And so their path through the column, if you're small, is going to be a lot longer because you're spending a lot of time inside these balls. Right? And if you're bigger than this pore size, you're not going to go in there. You're just going to go on the outside of all those balls, and your path hopefully will be shorter. So when you look at a chromatogram from a size exclusion column, the things that come out first are the big things, and the things that come out last are the small things, because they spend longer in the column in those balls. Right? And so the relationship between when you elute is directly proportional to your molecular mean diameter molecular size. And there's a relationship between molecular weight and size, and that's what determines whether you go in and how often you go in. So size exclusion is simply doing that. It's excluding, eluting analytes or molecules based on their size. Okay. And I've already asked you on a quiz, in size exclusion, who comes out where? You say, well, the bigger guys come out first because they don't get these balls, they spend less time that they're going around, and they come out first, and the little ones are all trapped inside of it as they're trying to get out of the column. That's a great hint.
How is the size detected?
How's it? How you detect this?
Yeah.
So the detection of what's coming out of here, and the detector is typically just like, because these are oftentimes these are biological molecules. So you might be using just a ultraviolet detection at a wavelength of 230, 280, which is just detecting typically the peptide bond that absorbs at that wavelength, or maybe some aromatic residues on amino acids that these proteins typically might take. So it's a bulk detection of just some absorbing species, typically it's absorbents that's being used. Okay. And then ion chromatography, of course, you know all about that, right? That is essentially looking at the relationship of how ions, and you're doing anion exchange, because you're exchanging the anion, which is your analyte, with the stationary phase. Of course, if we wanted to separate cations, it would be the exact opposite. The stationary phase would not be quaternary ammonia, it would be some anionic species, right? And your analyte would be cation. And anion exchange is just the it's just being facilitated by the electrostatic interactions and partitioning between the analyte and the stationary phase. Yeah, stationary phase. So you can look at this kind of a scheme like this and say, all right, let's kind of put it all together. I have here the exclusion kinds of chromatography where gel permeation and gel filtration are sort of, they're very similar. Right? And these are separating things based on excluding things going into a space based on their size. Right? So these are exclusion kinds of separation schemes versus partitioning. Right? And so reverse phase, normal phase, ion exchange, those three kinds that we just talked about, are all based on partitioning on the analyte with the stationary phase functional group. Right? So it's a chemical interaction, a chemical bonding interaction, electrostatic, dipole, or whatever we'll talk about that. Filtration, exclusion is not, right? It's just based on the physical size. And in fact, and this is a problem, in most size exclusion kinds of separations, sometimes there is a a chemical interaction between the analyte and the matrix, the size exclusion matrix. And that's a problem, because then you can't control that, and then the relationship between size and elution time, or retention time, is altered, because you've got some other kind of interfering effect of chemical interaction with material. Right? And a lot of times when you start doing a size exclusion, you have to first try to demonstrate that there's no chemical interaction, like hydrophobic interactions or hydrophilic interactions between your molecules you want to separate in the matrix. So you can look at a cartoon thing like this, and so this is size, right? So if you got really big things, these are molecular weight. If you got really big things, you're not going to be doing partitioning chromatography, because it just gets too complicated, because the bigger something gets, the more complex the chemical character of that molecule is, right? So when you get the really big things, you're really stuck with trying to separate those by some kind of exclusion methodology. When you have the small things, then you can start looking at partition kinds of chromatographic separations. And depending on the chemical character, whether it's nonpolar, then you might think of using some kind of reversed phase chromatography, where the stationary phase is also nonpolar. Okay? And if it's polar, or ionic, highly ionic, then you do the opposite, like you guys are doing. Because you can probably use some kind of ion exchange. So you can have a little graph like this and say, all right, my analytes are kind of like this, and about this side, it looks like I should be using blah, right? That people actually do that. Use figures like this to kind of help through that, what additional approaches you can consider. Okay, so we sort of talked about this. This is just a cartoon representation of what those interactions may look like. So if we start in normal phase here, in normal phase, the stationary phase is what? Polar, non-polar. It's going to be polar. I remember right there, I haven't erased it yet. Okay. All right, it's going to be polar, right? That's what these green things are supposed to be. It's a polar functional group. And here's your molecule that has a lot of carbon and hydrogens and an oxygen. And it's going to then partition with this polar stationary phase, depending on what the chemical composition of the mobile phase is, and what this is, and what the stationary phase is, right? In reverse phase, you see now you've got a lot of, in this case, the C8. So you should name these 1, 2, 3, 4, 5, 6, 7, 8, right? So there's a C8 column, and the C8 means that you have an 8-carbon chain that's attached to this stationary bead. And of course, carbons are very hydrophobic, right? We know. And so in reverse phase, the stationary phase is nonpolar, obviously. And then we have the same molecule in the mobile phase. And you might ask, how can you separate the same kind of molecule as in this cartoon in either a nonpolar or a polar stationary phase? How can you do that?
It'll just be the opposite that comes out first, right?
Well, that, yes. It's true, that's actually important. But you do that because the composition of your mobile phase is different, right? And so sometimes people will use either normal phase or reverse phase for the same kind of molecules, but it's the composition of the mobile phase, which of course is opposite what the stationary phase is, that really helps to drive that partitioning, so that selective partitioning. So here it's polar, non-polar, relatively non-polar multiphase, and then the opposite for reverse phase. And now, I'll talk about that in a second. Ion exchange, we're very familiar with this, right? We know this is, of course, is this an anion exchange column or a cation exchange column? What do you think it is? Anion exchange? Cation? Okay.
Because you're.
So what's the, it may be hard to tell because you can't tell what these guys are supposed to be, but what's the black here is what's supposed to be the functionalized group on the stationary phase, and you see it's negative, right? And so if it's a negative, that means it's attracting the opposite, and that would be the use of the cation, right? And so in this case, this is a cation exchange, ion chromatography, because the functional groups are the opposite of the cation in order to attract it, right? And so here, or maybe you're supposed to be mobile phase, sorry. Here's the anion, but still it's positive. And so here you have, like, in our case, you have some buffer, mobile phase buffer, that has a dissociating buffer that produces these cations that are weakly associated with the anions of the stationary phase that are outcompeted for by the stronger partitioning of the anion and cation with the stationary phase, right? We just talked about. So ion pairing is a very interesting sort of deviation of some of these methods. And you'll note that in this ion pairing example, we have a stationary phase that's a reversed phase. So it's a C8 in this example, a C8 carbon stationary phase, but we're using it to separate things that have an ionic character, And they do that because you introduce, in your mobile phase is something that's called an ion pairing agent that varies depending on the anions you're separating. And the ion pairing agent does this really interesting chemistry where it has this aliphatic character where it has both hydrophobic and hydrophilic character on two ends of the ion pairing agent. It hydrophobically associates with the C8 support in the stationary phase and exposes the, in this example, the anionic functional character of the ion pairing agent into the mobile phase space, where it can then interact with the molecules you want. And the advantage of this kind of a thing, you might say, why do that? Why not just do this, right? And the advantage of this is that you can actually titrate by having different concentrations of the ion pairing agent in the mobile phase, and which ion pairing agent you use, you can actually titrate the degree of these ion pairing agents that associate the stationary phase that are providing the separation. There's lots written on that, so I won't go into much more of that. Site exclusion, we already talked about that, so I won't go into it. Okay. Quickly, so stationary phase deserves, reverse phase deserves a little bit more of a mention because it's probably the most commonly used chromatographic separation scheme in chromatography. And I'd say there are probably about 75%, and that's maybe an understatement. But if you look at HPLC separation methodologies that are published in the literature for different kinds of experiments and whatever, I bet you at least 3/4 or more, maybe 80% of them, are reporting experiments utilizing reverse phase chromatography. So it's the most widely used, and partly it's the most widely used because some of the most widely reported applications of chromatography involve high performance or high pressure, we call it liquid chromatography, HPLC, and the vast majority of those applications are in the biomedical science field. That is. And in the biomedical science field, they're used to separate biological molecules, and biological molecules have typically varying degrees of hydrophobic character. And so reverse phase chromatography is very effective at separating biological molecules, all of which have some degree of hydrophobic character depending on the composition of the molecule. So we already talked about all this. So one thing that I want to point out is that the stationary phase typically varies. If you buy the column, it would either be a C4 column where it's only a 4-carbon chain, 8-carbon chain, or an 18-carbon chain. And the C18s are probably among the most commonly used. And so that's a very long carbon chain in that stationary phase that provides very strong hydrophobic characters to that stationary phase. So, separation. And in reverse phase, you're using this hydrophobic stationary phase in combination with a polar mobile phase. And that polar mobile phase is typically water, and mixed with some degrees of a relatively polar solvent, like nitrile and methanol or something like that. And it's that very interesting chemistry now with the water polar solvent mixtures of mobile phase with the nonpolar character of the stationary phase that determines what gets partitioned or separated. And I'll get to this right near the very end. In most cases of chromatography, they're using reverse phase. In general, they're utilizing what's called as a gradient elution. And that's versus an isocratic elution. And the difference between these two, an isocratic like you're using, in an isocratic, the mobile phase is constant throughout the elution. And in a gradient elution, just like it sounds, the mobile phase changes with elution. So if you were to look at, if I were to draw on this chromatogram, this is kind of, if I were to draw this chromatogram, the composition of the mobile phase over the elution time, elution profile, if I was doing isocratic, and I'll draw it up here, isocratic would look like that. It's constant. Right? You have one reservoir, with bicarbonate, carbonate, bicarbonate. So this is isocratic. But if I were to do a gradient elution profile, it would look something like this, where I would have one mobile phase coming in here, and then I change it, and the mobile phase composition would change. By the end of the elution, it would look like this. And so this is all mobile phase A. This is all mobile phase B. So I have two reservoirs that are being mixed by these fancy pumps. And the composition of A and B is changing in a linear fashion that I program in over the elution. And the advantage of that is that then you have the power to selectively elute compounds based on their partitioning with the stationary phase, in this case of a C18 column, and how that partitioning changes as the composition of the mobile phase changes. Right? So things that are weakly hydrophobic will stick to the column here. If this is water, let's say this is just water. We'll say this is methanol. Okay. Things that are very weakly hydrophobic will stick to the column here, but as I start putting even a tiny bit of methanol in, they'll partition into the mobile phase and they elute out. And they come out like that. And things that are strongly hydrophobic, more strongly, relatively hydrophobic, will stay in the column. They don't like the water, they're hydrophobic, they're partitioned to the stationary phase. They stay there until the mobile phase becomes relatively non-polar compared to water, right? And those things will elute out there. And depending on the hydrophobic character of the analyte, it's going to elute out at different places as the mobile phase composition changes. And this is really commonly done. And so this requires you have these two pump systems, these two reservoirs, and you program in, I'm going to go from 100% this to 100% that over this time. Sometimes you can do this, and then level off for a while to get those guys and do this, so you can program it any way you want. But by controlling the mobile phase composition in a reverse phase chromatographic separation, you have a lot of power to separate it. Otherwise, we would not be separated.
So rather than relying on time to eventually make
Well,
everything elute out, this is just exaggerating the separation?
it's both. It's relying. So within each, it's relying a little bit on time, but within each composition, let's see. So it's relying on time, but you're looking at it like once the mobile phase character changes, then the partitioning the relative partitioning changes dramatically. That's what you're banking on. And so when the mobile phase character changes, the idea about this gradient is you're trying to say, I want things that would otherwise be partitioned in a stationary phase, and when I make this more non-polar, they're going to now favor the mobile phase, and they'll elute out some time frame. It's just based on the flow rate and so forth, typically.
Is there any particular circumstance when you would do it stepwise as opposed to just like
Yes.
gradient?
Yes, because if you have things, depending on how many things you loop optimally here, 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 based on partitioning, is that maybe you might want to come up here, and you don't want these guys to run together, like that, let's say. You come up here, hold that for 5 minutes, here, hold that for 5 minutes, there's an infinite number of possibilities. And you sort of figure that out empirically based on what your chromatogram looks like. You see something, you see peaks running together, you change that gradient profile. Now the problem with these kinds of illusions is that these typically take 45 to 60 minutes. Which is kind of a pain in the neck. It's a long time. But if you're really interested in isolating these compounds, oftentimes when you're doing this, you're not just detecting them. You've got a fraction collector at the end of the electrode, and you're collecting. And each time, most HPLCs have a motorized fraction collector with a wheel with a bunch of small tubes on it. It's refrigerated. And every time a peak comes up, it knows how long it takes to get from when the peak detector senses the peak to the outlet of the tubing. And it turns the wheel, and it will collect this peak, and then when another peak comes out, it turns the wheel and collects that peak for you all automatically. You walk away with all these separated peaks. And you go to the NMR or whatever the mass spec to figure out who they are.
Well, to reduce that time, can you just change the flow rate of the column?
Can you?
Yeah. I mean, if
I'm
you-
asking the general question rhetorically. Can you, because in that logic, you say, I'm just going to turn it to 5 mils a minute, and I'll be out here in 10 minutes. And it's not a bad idea. People are like, but the problem is that when you change the flow rate, as you'll find on this coming week, is the separation changes. The peak shapes change, and the faster you go, peaks don't get eluted as effectively, and you start loading things together. And so that's all, if you had a chromatogram like this, you'd be like, yeah, I'm going to speed this thing up, because all I got is 2 peaks that are pretty far apart. But a lot of times you'll have like that.
Right. But like at the same time, if you change the gradient, you make it, let's say, like less aggressive gradient, you can still.
Yeah, that's right. And I think that is, and so we, not lately, but we used to do a lot of HPLC of biological compounds, and it is, you could spend, and the students would spend a week trying to optimize the combination of the gradient, the composition of the gradient, the flow rate, all these things to try to get that separation, sufficient separation in the shortest amount of time. It's very, it's kind of fun, but every iteration takes an hour. So you're like, okay, I can do this 10 times today because I'm going to work 10 hours. And I got to do tomorrow. And so, but that's what people do. That's exactly what it takes. Is you get in there and you see what it looks like, and then you start manipulating some of these parameters empirically to look at what kind of separation. And this, of course, this profile, of course, varies from one C18 column to another. I buy one from Dynex, I buy one from Waters, I buy